Thank you very much for the introduction, and I thank also the organizer for this invitation, giving me the chance to be here among you to discuss about the future of the terahertz, and also giving me the chance to come back to Germany, since, as the chairman said, since a few weeks I'm now in Greece. I moved from Germany. I have accepted a position in the Aristotle University of Thessaloniki in the Department of Physics, and I plan there to start also terahertz activities. So I hope. So, but mainly the work I will show you today, it has been done in the University of Martin Luther, where is my previous affiliation, in collaboration also with Berlin, and also in collaboration with my colleagues in Kaiserslautern. So, we have seen already in these first two talks the current status of the terahertz technologies. We have achieved as a community a lot in the past years. Many efforts have been done regarding materials, multi-layers, tri-layers, materials that are embedded in photonic crystals, using magnetic fields, not using magnetic fields as we just saw, synthetic magnets, different ideas that show really the capability of our field. This, I think you saw it in the morning from Tom. Okay, I saw it as a kind of achievement of the field, really this huge 1.5 mega electron volt per centimeter in this structure which is embedded in this dielectric mirror. Tom presented this recent publication of the group in Berlin. So it's not only that we are able to achieve such high, sorry, it's this. I'm confused with this now. Sorry. So we are aiming for really strong, strong signals, but also another good property of the terahertz emitters is that they are more or less independent of the wavelength that we use to excite them. So we have seen this in different wavelengths, and in a recent publication we try to go even further in the PAM wavelength, and you see more or less there is a kind of a plateau where the terahertz emitter works quite nice and then starts after 2000 nanometer to degrade. And this is very good also for applications, since we are here to discuss also possible applications. These systems, our emitters, can be integrated in femtosecond fiber laser systems that are commercial. So this is the status. Now another graphic trying to summarize everything. Okay, we deal with materials, with material properties, with the geometry of the systems, with electrical and optical properties of our construction. We have friends in theory, do simulations, also among us here. Our aim is to have, from the physics that we know, to get now to applications with higher signals, higher broadband, and also try to adjust our signals to the corresponding application. So I would summarize that the trend nowadays is to utilize the flow of heat and light, and this new trend that was also presented this morning to use of the orbital moment. But today I want to talk to you about materials. So I don't know why it has this time delay. So I want to talk to you about materials, and yeah, to give you another aspect. I think this is why we are here today, to see different aspects of the field. But of course you will tell me, Evangelos, materials, what materials? About materials everything is known. And here I show you from this, also from the Berlin group from 2016, this very nice graphic where, I mean, we all know that the signal we get depends on the spin Hall angle and on the magnetization of the sample. The spin Hall angle depends on the material. It's material dependent on the non-magnetic material, and you see the strength of the signals. Platinum has the first place, tungsten is the second. And so this is known. This is proven many times in the literature. And also concerning the magnets, so the magnetic layers, here's data from our lab. You see that iron compare here iron 2, platinum 3, all the same thicknesses. Iron is also the strongest one, following cobalt, and nickel is the lowest one, but now has also another perspective concerning the orbital moments. So this is known. Okay, so what I can show you today, different. Usually, this is the case that the literature, most of the people use. This is the cobalt iron, the tungsten, cobalt iron, boron, platinum tri-layer. The tri-layers, because of this opposite spin Hall angles, show the highest signals. Still, I want to talk to you today about materials, and I will try the tantal case. And why the tantal case? Because we try to make a series of iron tantal. You see in this graphic, tantal has small terahertz amplitude is expected because of its small spin Hall conductivity. And we made a series, and we were expecting that the tantal 3 nanometers, iron 2 nanometers would have the highest signal, because we know, this graphic you saw also in some previous publications, that we expect, so the emission, the terahertz emission is thickness dependent. We expect a maximum of the emission of total thickness of 5 nanometers. And this is what we try to do. We have shown this in iron platinum. Many people have seen this thickness dependence of the signal. However, I mean, we get a signal, a small signal for tantal. However, when we went to thinner tantal layers, we saw a drastic increase of the signal. And this was a kind of a triggering of doing more research on it. So the tantal 1.5 nanometers, iron 2 nanometers gave us 3-4 times higher signal than it was expected. So this enhancement triggered us to go further and try to make the tri-layers. And here I compare in this graph the iron platinum bilayer with the tantal iron platinum bilayer, and on this axis you have the thicknesses of the non-magnetic layers. Okay, and you see that the tri-layer is above for 1 and 1.5 nanometer. The 1.5 nanometer is the one that exhibits the highest signal I showed you before as a bilayer. At some point they are comparable, the terahertz amplitude, and then it decreases. So the tri-layer is higher than the bilayer, as to be expected, as for the case for the tungsten iron platinum, for example, or the tungsten iron cobalt boron platinum, but not for the thicknesses that we were expecting. I'm sorry for this delay. I don't know. Yeah. So the enhancement, as I said, for very thin tantal thickness. And then we said, okay, what can happen? And I will show you now maybe a reason. Okay, so we went and performed structural analysis of our samples. And the best sample, I present you the best sample, the 1.52 nanometers, the tri-layer. So in this field, this type of electron microscopy, high resolution electron microscopy image, where in principle I show you an image where the contrast is only dependent on the atomic number, the difference of the atomic number. We have also diffraction contrast images where we can see the very good epitaxial growth of tantal on MgO, and then the iron and the platinum in this epitaxial relation. So tantal grows epitaxial on MgO, iron rotates 45 degrees its lattice, and then platinum fits on top of iron. However, the new thing that we discovered is that this form of tantal does not normally exist. So everybody knows about the alpha phase of tantal, which is the BCC phase. People in the Spintronics try to make the beta phase of tantal, which is this tetragonal distortion, this metastable tetragonal phase. But the FCC phase is as we call it, allotropic phase. It's an FCC phase, and I think we let now the theoreticians to try to calculate the spin orbits and the spin band coupling here in order to see, to explain our data. So this is the one, the first, let's say, result of how I want to show you about new materials, about this new phase of tantal, and then I will move on to the alloyed interface. So what else did we try to do? We took our bilayer, our platinum bilayer, and trying to grow at the interlayer an alloy. And we managed to grow this L10 ordered phase of iron platinum. Here you see the transmission electron microscopy images. So, and this is, for the magnetic people, it's very known. It's an old friend. People tried in the past and nowadays to fabricate this alloy because it's one magnetic material with the highest magnetic anisotropy. So here you see also the structure. In principle, the iron atoms meet this layered structure of the L1 phase ordered iron platinum. So, and now I will compare the terahertz signals of this special structure, and you see that you compare the bilayer and then the trilayer with the alloyed interface in between, and you see that the alloyed interface, the trilayer, has a high signal, terahertz signal. Same form, same waveform, same bandwidth, but the highest signal. So this is one result that we recently published. However, as I said, I repeat again this thickness dependence. When we try to do these samples, we were, as growers, we were trying to go to higher thicknesses. So this is a total thickness of 17, 18 nanometers. This absorbs terahertz. So we try to do now to be at this peak. So we try to induce the alloy at the 5 nanometer thickness. And this is what we did. This is really new data. So you see that in the total thickness of 5 nanometers of the alloy, we again achieved, with our growth technique, to induce again this L10 phase at the interface. And it's not only this. This is a special structure which I would say surprises us. And we did some phase analysis of our electron microscopy images. And in principle, you can have a look at these two graphs which come from this analysis. So here we look at the strain that is induced along the along our sample. So we are looking at here the strain that is induced along this is the growth direction. This is the growth direction, and along the in plane. So along perpendicular to the growth direction, and you see a very strange behavior. So here, in principle, out of plane, you can see that you start with MGO. Our reference. This is the strain that is induced induced from this relation, where we have the strain of the layer above the substrate, and here's the substrate. So we use a reference the substrate, and using as a reference the substrate, we see that out of plane we have the strain that corresponds to iron, then gradually goes to the alloy here, and then goes back to platinum. And then the very interesting thing is that the in-plane strain seems to be just one. And this indicates that we have a kind of a pseudomorphic accommodation of platinum in the alloy. So in other words, I would say it's a kind of a continuous alloy. So not an alloy, a kind of a special structure of continuous alloy. Does this structure give us a good terahertz signal? So in principle, yes. So again, we see the same. So the highest curve is the sample which I call with this alloyed interface with the data I saw before, the structural data, and it's above the bilayer. And if you try to go high to make the alloy in the volume, then you again decrease the signal. So the conclusion here is that the ordered L1 phase as an interface even keeps the highest signal, the terahertz signal, even for the thinner samples. So the take-home message from this first part of my talk is that I want to say that there is, I think, still plenty of room for materials for the spintronic emitters. We don't know still everything, although of course we know how to move, but I think there are still surprises, as the two examples that I just gave. In the second part of the talk, I will go from the spin Hall angle and from the magnetization away, and I will focus on the charge current. And in the charge current dynamics. This is a work which has been done in Halle in the framework of this SFB research project, ultra-fast spin dynamics, where I was involved. The driving force was Professor Georg Schmidt, his PhD Bikas Mohapatra, and it's in collaboration with the group of Tobias. Measurements that I will show now have been performed in Berlin from Reza Ruzekar. So the question here is the charge dynamics. Nobody takes care about the charge dynamics. In which sense? So here you see the question we pose is what happens after all of this spin current situation, after the laser induces the inverse spin Hall effect, and then we have the charge current. So what happens after the spin to charge conversion? What happens to the charge current itself? So if you make a simulation, and here is the laser spots, and here we plot the charge current density along a specific direction, you see that there is a massive charging at the edges, at the left, or let's say the edges, left and right hand sides. And this and after some time, this massive charging diffuses, and in principle, if you see here, after some time, you even have here you have even a backflow of the current, and here you have even a backflow inside the spot where you illuminate. So this is what we try to show here with this curve by showing that we have you see the total current is what we detect, this bipolar pulse. This is the total current, but it comes as an addition from two parts, the main induced current induced by the inverse spin Hall effect, and then you have a kind of a response current or backflow current, which is the blue curve. And the addition, the convolution of these two currents give us this shape. And the main argument is that this happens because of this restoration of the charge neutrality. We can explain this effect in terms of a simple RC circuit. So in principle, what do you have? You have your laser, you charge, you induce your spin current, then you have the charge current. The charge current charges this your metal film, and then you have a kind of discharging. So it's like you, with your initial current, you charge a condensator, and then you discharge the condensator with this backflow current. And we can describe this mathematically with a simple relation from the first years in the university, we know. And this is the response or the backflow current that happens outside the beginning, but also inside, and opposes the initial current that we have. So what this gives, if we get if from this relation now I go to the fast Fourier representation of the effect, we get to this relation where the total current depends on the initial current that you have, but it is shaped from this filter function, we call this function, which depends on the resistance, on the conductivity of your metal, on the capacity of your metal sheet, and on the frequency. And on this frequency, of course, comes also the impedance of the whole system. So, and this results, it's a kind of a function, as a high-pass filter function. We have a kind of we're expecting a kind of a cutoff frequency, and yeah, it's a high-pass filter. So the high-frequency components pass through the capacitance. So we saw this again in modeling. Still, up to now, it's still modeling, and you see this. The red curve is the expected initial current, and this is the high-pass the high-pass filter function of this effect. So, and this charging effect depends. We have studied this by changing the spatial profile of the laser, the temporal profile, and also changing the conductivity of the material parameters. So we have seen this. And The question now, and this is the last thing I want to say, is how, because this was so far a modeling, this was a kind of thinking of the charge dynamics and trying to simulate it. But can we really see this? Because nobody has seen it. So we think we can see this by going to nano-patterning. So we pattern our emitter, our continuous film, in small structures. You see here in this range of 1 micrometer, different sizes, square, and different shapes. So, and this, by having this charging now at the edges of our nano element, we hope we will be able to see this filter function and the backflow. As I said, it's different shapes. So indicative, I saw some results. This is pulses. The up here is the continuous film, and now is the different square sizes. Now I saw only the square sizes here of different sizes. You see the spectra. The black it's better because we don't have a lot of time to look at this C. Here is the reference. We always compare with a continuous film. We always compare with a continuous film. And then you see that there is a drop of the signal is expected. We have less material on the surface. But then we have 3 regions for that we can see that there is a drastic change in the shape of the spectra. So this is the low filter, the high-pass filter function, okay? So low frequencies are cut. But also there are some characteristics at specific frequencies that are really derived from this charge dynamics and the backflow current. Again, we can explain the physics based on this RC circuit, and then we can add, if we have kind of coupling between the elements, we can add another capacitor, coupling capacitor, which is indicated as CJ here. And in principle, again, we have the same concept, even in the nano pattern, and even if there is a coupling, you have the total current that you get is a kind of convolution of your initial current and their filter function that has now more capacitance components and more resistance components. So then this thing can also depend on okay, it's a high pass function, you saw it. Depends not only on the material parameters, but also on the geometry now, if we go to the nano patterns. And for more details, we can discuss later during the conference. So this is my summary. I show you that the new materials, we can go for new materials for manipulate engineering interfaces in the direction of growing the signal, our expected terahertz signal, and also that we can also have a look at the charge dynamics that are coming after the spin dynamics, and also can play a role and can shape the bandwidth of our signal. And with this one, I would like to thank my collaborators in Kaiserslautern, Professor Beigang, Director Ocean, my student Laura Sawyer, the group of Professor Smith. We spent 4 years together in Halle, and then Professor Masahiko Tani in Japan, Professor Schneider in Kaiserslautern, Professor of Bill in University of Arizona. And with this one, I want to thank you for your attention.